In this video, we continue with Chapter 4.4 examples, taking a look at spanning sets. Our learning objective is to determine whether a spanning set that we call S of vectors in a vector space is a spanning set of the vector space V. So in our definitions, we are going to let S equal the vectors V1 through Vk, and that is going to be a subset of a vector space V. Then we say S is called the spanning set of V if and only if every vector in V can be written as a linear combination of a vector in S. So in such cases, we say that S spans V, and we say the span of S is V, the vector space. So we're going to be using the linear combination skills that we developed in the earlier video. So here are some examples of spanning sets. So if you think about the set 1, 0, 0, 0, 1, 0, and 0, 0, 1, it's easy to see that that set spans R3 because any vector in R3 can be written as a combination of the vector value times 1, 0, 0 plus the vector value in space 2 times 0, 1, 0. And the vector value in space 3 times 0, 0, 1. Similarly, the set 1x and x squared span P2, the set of polynomials of degree 2 or less, because any vector, which in this case is a polynomial, in the form P of x equals ax squared plus bx plus c, can be written as a combination of 1x and x squared added up. So we would say P of x equals some coefficient c times 1 plus some coefficient v times x plus some coefficient a times x squared. And of course, because the vector space is polynomials of degree 2 or less, you could have a coefficient b 0 and just have a linear equation in there. You could also similarly have a and b be 0 and just have a constant in there. Okay, so let's take a look at an example here. We are going to determine whether this set that we're going to call S1, which is vectors 5, 7, 6, 4, 2, 4, and 1, negative 3, 2, spans R3. R3 consists of all the vectors of the form v1, v2, v3, where v1, v2, and v3 are real numbers. So the three-dimensional vectors in three-dimensional space. So S1, we are going to be able to say spans R3 if we can always solve for the scalars C1, C2, and C3 in this equation. Any vector equals some constant C1 times this vector 5, 7, 6, plus some constant C2 times this vector 4, 2, 4, plus some constant C3 times this vector 1, 3, 2. All right, so let's distribute the constants through. So we get 5c1, 7c1, and 6c1 in the first vector part of the addition here. 4c2, 2c2, and 4c2 in the second part of the vector addition here. And 1c3, negative 3c3, and 2c3 in the third part of the vector addition here. And then let's rearrange and add up all the first elements. So pulling out the first elements from each of these vectors, we get 5c1 plus 4c2 plus 1c3. Similarly, pulling out the second elements from each of those vector elements, we get 7c1 plus 2c2 minus c3c in the second position. And then pulling out the third elements, we get in the third position 6c1 plus 4c2 plus 2c3. So we are going to rewrite this as a system. So this is equivalent to saying, well, element V1 equals 5c1 plus 4c2 plus 1c3. Element V2 is going to equal 7c1 plus 2c2 minus 3c3. And element V3, the third element in our vector, is going to be a combination of 6c1 plus 4c2 plus 2c3. So let's translate this to a matrix. So that's this matrix equation with our coefficients here multiplied by our scalars, C1, C2, C3, equaling our vector v elements v1, v2, v3. All right, now we're not going to be able to go type this into SIMPy because we don't have a set of solutions for v1, v2, v3 that we're specifically solving for. We're trying to determine whether this set spans R3. So we need to think about, well, can this equation be solved or not? So think back to theorem 3.3. So we are able to say that this equation can always be solved for C1, C2, C3 because the determinant of the coefficient matrix is not 0. So the matrix is invertible. You can go check in SIMPy, the determinant is negative 32. So because of that, we're able to conclude that S1 spans R3. So let's get a little bit more into our reasoning here. So when the coefficient matrix of the system has a non-zero determinant, like we have right here, it follows from that list of equivalent conditions that we had back in section 3.3 that the system has a unique solution. So any vector in R3 can be written as a linear combination of vectors in S, and you can conclude that that S spans R3. And so that's because we're able to show the coefficient matrix here as a non-zero determinant. So let's check another example. So this is almost the same set, except we're changing the value in the second vector to lead off with a 3 before this was 4. So let's see if we make that change. Does this new set, S2, still span R3 or not? All right, so we can still solve this equation of v1, v2, v3. We're going to say v1, v2, v3 equals c1 times the vector 5, 7, 6 plus c2 times the vector that is now 3, 2, 4 plus c3 times the vector that is now 1, negative 3, and 2. All right, and so the equivalent equation, if we put it in matrix form, is going to look like this. We're going to have 5, 3, 1 in the top row, pulling these elements from the first components. In our coefficient matrix, we're going to have 7, 2, and negative 3, pulling the values from the second position. And in the third row, we're going to have 6, 4, and 2. That's going to get multiplied by our scalars, C1, C2, C3. And that's going to equal our V1, V2, V3. So we just need to check if this coefficient matrix is invertible, or in other words, is the coefficient matrix equal 0 or not? So if the coefficient matrix is not 0, I'm sorry, if the determinant of the coefficient matrix is 0 or not. So let's check the determinant of the coefficient matrix. So determinant of 5, 3, 1, 7, 2, negative 3, 6, 4, 2 does in fact equal 0. Okay, so that means the matrix is not invertible. And so that means that we do not have a unique solution, right? If we go back to thinking about our equivalent conditions, the system having a unique solution is equivalent to a non-zero determinant. So we can say the system does not have a unique solution. And you can think about that because we can't invert the matrix to solve. And so S2 does not span R3. So here's a visualization of S1 and S2. So S1 from our first example, we can see that the vectors in S1 are not in the same plane. They are spanning all of 3D space here in this first image. But if we look over at our second image diagram here of S2 vectors, those are all in the same plane. And I know it's hard to kind of look at my 3D images here online, but hopefully you can see the kind of plane drawn out here to show that these vectors from S2 are all in the same 2D plane here in 3D space. So if we want to have a spanning set of R3, we need a three-dimensional space for our vectors like we have with S1. So we can see, okay, if our vectors kind of need 3D space and they span R3, but if they fit in a plane, they don't span R3. And then I put a note down here. So although the set S2 does not span all of R3, it does span a subset of R3, this should say the plane in which the three vectors of S2 lie. There you go, now it says plane. The subspace is known as the span of S2, and so we are going to use this to define the spans of sets. So the span of a set is defined here. So if S is vectors v1 through vk, and that's a set of vectors in vector space V, then we can say the span of S is a set of all linear combinations of the vectors in S. So the span of S equals C1 times V1 plus C2 times V2, all the way through adding CK times VK, where C is a scalar, so C1 through CK are scalars, and V1 through VK are vectors in vector space V. So we sometimes write the span as span, and then in these squiggly brackets, we list specifically the vectors. Instead of saying span of S, it's your choice. There's another notation that we're not going to use because it's going to get confusing later when we do some more calculations. It uses these brackets at either end. So we aren't going to use those because we'll be using those later for dot product calculations and other calculations. So the next theorem tells us that the span of any finite non-empty subset of a vector space V is also a subspace of V. So this is theorem 4.7. So if S is this set of vectors V1 through Vk in a vector space V, then the span of S is a subspace of V. And then moreover, the span of S is the smallest subspace of V that contains S, in the sense that every subspace that contains S must also contain span of S. So it's important to note that these are non-empty sets of vectors. If it was empty, then all bets would be off. So you have to assume that it's a set with some elements. 0 could be an element, but it can't be an empty set. So let's take a look at our proof. So to show that span S, this set of all linear combinations of the vectors v1 through vk is a subspace of V, we want to show that it's closed under addition and scalar multiplication. Remember back to last week when you studied showing subspaces, you had to show closure under addition and scalar multiplication. All right, so we're going to take two vectors u and v that are in the span of S, and they can both be written as linear combinations of the vectors v1 through vk. So for vector u here, we're using c's for the coefficients. And for vector v, we're using d's for the coefficients, or you can call them scalars. So c1 through ck and d1 through dk are scalars. Then if we continue over here, when we add up u plus v, because they both contain vectors v1 through vk as sums, our scalars or coefficients just become c1 plus d1 multiplied by v1, c2 plus d2 multiplied by v2, all the way through ck plus dk multiplied by vk. And then if we do scalar multiplication, if you multiply a scalar c times vector u, you get c times c1 multiplied by v1, and then that same scalar c times c2 multiplied by v2, all the way through C times CK scalars multiplied by VK. And we get a similar if we multiply this scalar through by vector V. So this means that U plus V and CU are also in span S because they can be written as linear combinations of these vectors V1 through Vk that are in S. So we are able to conclude that the span of S is also a subspace of V. Now we want to show this second part, that span S is the smallest subspace of V. So now we're going to prove that span S is the smallest subspace of V that contains V in this part here. So suppose U is another subspace of V that also contains S. Then to show that span of S is in U, let little u be a vector, be in span S. Then we can write U as a sum of the scalars C1 through CK times V1 through VK. If we expanded this, this is just C1 V1 plus all the way through CK VK. So this sigma is just notation to show that we're adding up 1 through K, where all of the V's are in S, and so the VI is in U, and that's because U contains S, and then because U is a subspace, vector U is also in U. So that shows that S is the smallest subspace of V that contains S. I think I needed to say here S, not V. Yeah, there should be an S here, not V. I need a typo. So what we showed is that S is the span of S is the smallest subspace of V that contains S. Is that right? Let's go back. Yeah, the smallest subspace of V that contains S right here. Okay, so I made a typo, we got it fixed. All right, in the next video, we are going to look at linearly independent and linearly dependent sets of vectors.